We wanted the ability to build something that nobody had ever conceived of before. Like, everybody knows a car has 4 wheels, an airplane has wings, but what does a Hyperloop have? Right, Hyperloop could have anything we imagine. The idea of being able to take what is the best features of some of the other modes, keep them, get rid of all the other aspects, make something sustainable, make something long-term that truly redefines the way that we move. I would sign up for that 1,000 times out of 500.
A global technological revolution is underway.
We think in the next 10 years, you'll see more innovation than we've seen in the past 50.
Driven by passionate, dedicated individuals intent on shaping a new world.
I want to create something new. I want to create something that gives me the sense of creating new life. This is why I'm here.
A greener world.
This is the last call to action, that we have to develop the solutions that are protecting our planet.
A better world.
I have a family, and when I think about the life I want them to have and their children to have, I want them to experience the world where they can travel and live without worry, and that gets me up and going every day.
Together, they are pushing engineering to its limits.
Human creativity is the most tremendous power, and if you set a target, things that you never thought possible become possible.
Creating extraordinary machines that can help the planet and humankind in the future. In April 2018, 24 large steel tubes were fabricated in Spain, then trucked across the border to France.
We were thrilled to see this coming to life. So we were literally driving behind the trucks, these oversized load trucks with the 4-meter in diameter tube.
In Toulouse in southern France, the tubes were assembled into a test track.
After years of dreaming about it, drawing it, talking about it, engineering it, to see it finally come together was really something that was extraordinary for us, for the team, and I think for the world as well.
Rob Miller works at Hyperloop TT, one of several companies developing an entirely new way to travel. It's called Hyperloop and works by propelling levitating vehicles rapidly through tubes, carrying passengers or cargo. The capsules can travel between cities and countries that are currently many hours apart in a matter of minutes.
We call Hyperloop the 5th mode of transportation. The safe, fast, more sustainable form that uses a lack of friction and a lack of drag for us to travel in capsules and tubes at high speeds.
The race to build a Hyperloop was triggered by a famous billionaire who doesn't shy away from big engineering challenges. He announced the idea during an online chat show in 2012.
I have a name for it, which is called the Hyperloop.
The Hyperloop?
Hyperloop, yeah.
Is it like a Jetsons tunnel?
It's something like that, yeah. It goes about, let's say, an average speed of twice what an aircraft would do. So you go from downtown LA to downtown San Francisco in under 30 minutes.
Mm-hmm.
Anyways, that's...
Do you think this is possible? This is not just...
Yes, absolutely, absolutely, yeah.
The following year, he published a white paper with a detailed proposal called Hyperloop Alpha.
So the design proposed in the Alpha paper is essentially tube travel, low-pressure system to eliminate drag. And at that time, Elon Musk said in public that this was something that needed to get done. He was a little bit too busy, so he open-sourced the white paper and said, anyone who's out there who wants to give this a try, please feel free.
The idea inspired engineers around the globe. Here was a chance to solve one of the world's biggest problems, the rapidly growing carbon emissions from transportation, while allowing faster travel than ever. Hyperloop offered a way to move people and goods in less time than a plane with the convenience of a train and with potentially zero carbon emissions.
If we can bring airplane speeds to the ground sustainably and safely, what Hyperloop does would be a real benefit to society.
The engineering challenges are immense, and it will be many years before a paying passenger steps on the first Hyperloop. But the rewards could be enormous. One study suggests a nationwide Hyperloop could boost America's GDP alone by $200 billion. The race had begun to prove this transformational technology was even possible. The first company off the blocks was Hyperloop TT.
2 weeks after the white paper was launched, we put out a call to action for engineers around the world, and we had this overwhelming response of not just anybody, of engineers and technologists that had already done amazing things. Everything from the CERN Large Hadron Collider to the Manhattan Project. So it was this incredible team, but we chose 100 engineers to work on this, work on the feasibility to see if the this Hyperloop thing was actually possible. The conclusion was that this is not only feasible, but it can be done with technology that exists today.
The company set out to design and construct a revolutionary new transportation system. As well as the tube, they've built a prototype capsule that can carry up to 50 passengers. But for a Hyperloop pod like this to reach ultra-high speeds, they need to address the factors that slow down other kinds of vehicles. Drag from air resistance and friction caused by contact between wheels and the ground. The team's first challenge was to eliminate friction. Floating trains called maglev already exist in China and Japan, but their powerful electromagnets require a huge amount of electricity, making them fast but expensive and energy-intensive to operate. So Hyperloop TT are developing a next-generation maglev that can levitate without the need for any extra power at all.
The secret sauce of our passive magnetic levitation system is a Hallback array. And what a Hallback array is a series of permanent magnets arranged in a certain way, almost like a cheat code on a video game, up, down, left, right, left, right. If you arrange it a certain way, you get a enhanced and directed magnetic field.
When a Hallback array moves over an aluminum track, the strong magnetic field induces electrical currents inside the metal. And that turns the track temporarily into an opposing magnet. The repulsive force lifts the magnets up by over an inch, along with the capsule. The team have also installed vacuum pumps to remove 99.9% of the air inside the tube, reducing air resistance to almost nothing. Together with the levitation, Hyperloop TT believe this will allow them to reach speeds of up to 760 miles per hour. And the Hyperloop will not only be fast, but extremely efficient.
You almost completely reduce friction, you almost completely reduce drag. So once you're up to speed, you'll still be traveling without any energy use. For us, it's as close to perpetual motion as you can get.
The US Department for Transportation estimates that Hyperloop routes could be up to 6 times more energy efficient than aircraft on short routes. That means a much smaller carbon footprint, and the power it does use can be clean and green.
We're fully electric and we're fully emissions-free. So building a propulsion system, it's a must that the capsule be all electric, and our system is that today.
Hyperloop TT are still preparing to demonstrate their system in France. But thousands of miles away, Hyperloop pods have been flying through a tube for some time. 2 years after his white paper, Elon Musk had a scaled-down Hyperloop track built at SpaceX HQ in California, 6 feet wide and 3/4 of a mile long. Then he put on a contest for students to design, build, and race the best miniature pod.
What this is really intended to do is to encourage innovation in transport technology. And I think we'll find that it's way more incredible than we ever realized. And then later today, we'll see how fast the pods can go. So congrats to everyone. I'm amazed at what the student teams have done. really just blown my mind, and may the best team win. Yeah.
Over 1,000 teams entered, with 30 finalists selected for the competition weekend. One of them was from the University of Delft in the Netherlands, including mechanical engineering student Tim Houter.
When we got to hear about the concept, we already thought that it was something that could completely change the world in terms of mobility, but also in terms of sustainability. And that we also really like engineering challenges. So when the competition came along, we didn't have to think long in order to also set up a team. And it was a really intense period because you need to achieve very high technical standards in a really short amount of time. So together with that whole team, it was basically 24/7 of work, where some people also continued to work during the nights to make sure that we met our deadlines and that we could unveil our Hyperloop prototype on time. The different categories that we could score points for were the efficiency of your vehicle, the safety, the cost, but also the speed that you were able to achieve. And we took all those criteria into account and designed a vehicle that would have the highest overall score on the combination of all these aspects.
The team finally unveiled their design in June 2016.
One of the dummy passengers, we called him Elon, referring to Elon Musk, of course.
Once in California, the teams had to pass a series of challenges to qualify for the last stage. Operating in a vacuum, being propelled along an open-air track, and moving through the tube at normal pressure.
Only if you have passed those tests, you were allowed to proceed towards the final test run that would then eventually determine the winner of the Hyperloop competition.
Only 3 teams qualified for the final run in the depressurized tube.
When we had the confirmation that we were one of those, that's of course an amazing feeling and only makes you more excited to really give it as much as you can for that final run and go for the win.
Everything was set, but as the team carried out the last checks, there was an unexpected issue.
When we were almost ready, we actually noticed a malfunction of the braking system. And that was quite a terrifying moment, because your braking system needs to work, of course, before you can do your final run.
They hurried into the tube to investigate.
So you cannot wait too long before you do your run, otherwise you need to get out of the tube and make room for another team. So the pressure was really on to have it fixed.
After a few minutes, they figured out the problem.
Luckily, we got it fixed while it was standing there, but it was quite quite an exciting moment.
The speed to beat was 94 kilometers per hour, or 58 miles per hour, clocked earlier by Team War from Germany. Nowhere near as fast as Elon Musk had in mind for a future Hyperloop, but still a challenge in a short vacuum tube.
We're going to start the countdown right now. They said that they're basically ready, and we're excited to see how it goes.
5, 4, 3, 2, 1.
There was this very sort of tense moment, but then you see that everything is going smoothly and the vehicle's getting up to speed in the way that it should.
Delft Hyperloop had matched the fastest speed. They also scored highly in other categories, from design to safety.
The team with the highest score, the sum of all of the other categories, and that's Delft.
And it was really amazing. Everybody was extremely in excitement and cheering and hugging each other. That was really, really great.
Team Delft were World Hyperloop champions. Some of the team decided to take the next step to launch a company and develop a full Hyperloop system with a new pod and a new track.
We thought, well, this potential is so huge and we've built up such a momentum. Shouldn't we proceed with it and make it a reality in the real world?
Tim Houter is now CEO of Heart Hyperloop. After the competition, he and his colleagues faced a new challenge: To travel through a network of tubes that connect many cities, their new design would need to be able to switch lanes, something no one had done before.
The Hyperloop tube that was built by SpaceX for Elon Musk's Hyperloop competition only allowed you to go straight, but didn't have the ability to take corners or to perform this lane switch. So we need to do some tweaks on the Hyperloop concept that we have made for the competition.
The obvious solution would be to design a system similar to a railroad switch, which has a moving pair of rails called points. Even existing maglev tracks physically shift when trains need to change lines. But for Hyperloop, the team realized that mechanical switches would be too slow.
One of our core objectives was to have the ability to perform a lane switch without any moving components in the infrastructure, which enables this high speed.
To switch lanes with no moving parts, the team needed a new approach. First, they designed the pod to be suspended from above rather than from below. But that means the pod must levitate with an attractive magnetic force instead of a repulsive one, like the Holbach array. And this presents a challenge.
We have a magnetic levitation system. That means that we have a steel track on the top and a magnet on the vehicle. And if I bring it too close, it will stick. And if I bring it too far away, it will fall away. So we'll try and be in an equilibrium state where the magnet is not falling, but also not attracting.
Engineer Gert Speck was part of the team that built a small-scale levitation rig to see if they could keep the system in equilibrium.
So we found a way to alter the magnetic field, as we can demonstrate on our test setup. It will slowly lift up. We have a laser sensor here that measures the distance 2,000 times a second and feeds this back into the control system.
The laser sensor works in tandem with the magnets, which have copper wire wrapped around them. This allows the control system to boost or reduce the strength of the magnets depending on the distance measured by the lasers. And this keeps the floating pod in exactly the right place.
When I try to push it down, it will give a little bit, but bounce back up. Same way, if I push it up, it will weaken the magnetic field and then fall back down.
The laser sensor and adjustable magnets stabilize the levitation system. But if it adjusts for every bump in the track, the ride could get uncomfortable for passengers. So in February 2021, lead engineer Yusuf Harfouch set up a system to simulate traveling at 450 miles per hour.
A question that we often get is whether it will be a bumpy ride for passengers on board of Hyperloop vehicles, especially at high speeds, when the vehicle is traveling a few hundred meters every second in an infrastructure that cannot possibly be completely straight. In this setup, a Hyperloop vehicle is simulated by having both a levitating magnet as well as a hanging weight underneath, mimicking the cabin's weight. By placing the construction on a vibration table, we've simulated a situation where the vehicle is passing an irregular infrastructure at high speeds.
The control system is designed to intelligently smooth out any bumps in the track. But as the vibrations reached full speed, it wasn't responding as the team expected.
The first time we ran the test, it was not going perfectly smooth. There was a part of the shaker table that wasn't behaving the way we simulated it.
The team analyzed the data and adjusted the control system before trying again. This time, they turned the vibrations up to the max.
And what we see here is that indeed, the vibrations do not affect the vehicle or the stability of the overall system.
It was a great moment of success because we saw that the system, even though we were pushing the envelope way beyond what we expect in a real-life Hyperloop system, it was hanging perfectly still in mid-air, even though the shaker table was moving up and down a lot.
To make sure the whole system worked together, Hart built a short, full-width test track with steel strips on the sides. The capsule is suspended from above, which means electromagnets can easily pull the capsule left or right towards one of the strips. By June 2019, the team were ready to test the full setup.
Levitation in 3, 2, 1. Levitation successful. Youssef, propulsion. Propulsion, good to go. 3, 2, 1. Yes, propulsion successful. Switch in 3, 2, 1. Switch taken, switch successful. We have a successful test.
Public Affairs lead Juliette Delarue knows the benefits of the switching technology.
This is actually the first ever developed and patented Hyperloop lane switch. The system allows you to act more or less like a highway. There is no contact between components, and so there is no wear and tear. A vehicle can just easily choose its own destination, and without any moving components, this means that vehicles can follow up on each other quite easily in short time slots, so this can increase your capacity massively.
Hart's test track proves that Hyperloop capsules could one day navigate their way through a network of tubes. But their tube is much too short to reach the speeds that Hyperloop promises. However, back in America, another company is setting out to prove for the first time that a pod can be propelled along a full-scale track at high speed, and that it's safe for passengers. In January 2017, their team were assembling the world's longest full-width Hyperloop tube at 1,600 feet. Still not long enough to accelerate up to aircraft speeds, but potentially enough to surpass high-speed rail.
The nice thing about doing something that nobody has ever done before is that nobody can tell you how to do it. However, that's also a curse, is that nobody can tell you how to do it. So we learned, we tried different things. We made plenty of mistakes, but we also learned how to do things quite a bit faster. Like at the beginning, we could only install maybe 1 or 2 feet of track per day. By the end, we were installing 30, 40, 50 feet of track per day, and that was all because we were learning about the process.
Josh Geigel is co-founder of Virgin Hyperloop. Having previously worked at SpaceX, Josh read the Hyperloop paper by Elon Musk in 2013.
My initial read was like, this feels like a little bit of a crazy idea, and there were some mathematical errors in it that I jabbed my friends about. And shortly after that, I decided to look at that with a future colleague. And the idea of tackling a new idea in transportation really became powerful. The ability to build something that nobody had ever conceived of before. Like everybody knows a car has 4 wheels, an airplane has wings, but what does a Hyperloop have? A Hyperloop could have anything we imagine. So we started out in a garage in North Los Angeles in November of 2014. And the goal at that time was how quickly could we build a prototype, a piece of technology to show that this idea was even feasible. And that's what we really set out to do, is like, let's figure out what we can build to demonstrate that a Hyperloop is even possible. We looked at a lot of different places for a test track, and Las Vegas is pretty close to Los Angeles, and we picked the desert. It would get down to about 0 or -5 Fahrenheit in the winter, which was pretty cold. And then in the summer, it would be about 120, 130 degrees Fahrenheit.
The extreme swings in temperature would cause the steel track to expand and contract by over a foot. So the tube could only be fixed in one place. Along its length, the team installed rings to allow for expansion. And by elevating the tube above the ground, the Hyperloop track should have less impact on wildlife and the environment than a conventional rail line. By March 2017, despite the challenging weather, the team were building the test site at a phenomenal rate.
Today, they actually started commissioning the vacuum tent for the first time this week. And this is where we actually create the low pressure environment inside the tube. So this big setup you see is our actual vacuum system. So we have a number of blowers, pumps here at the top, and they come in, they suck through these 8 pumps, they come through these 2, and they eventually go through these 4.
The pumps reduce the air pressure in the tube to the equivalent of 200,000 feet of altitude, almost 6 times the cruising height of airliners.
So if you can see right now, they're actually installing the control system for this particular pump. And this is the first time they're actually doing this, so it's a pretty exciting day today.
Reducing air resistance is a key step towards achieving high speeds. But another critical factor is the propulsion system itself that will be fitted inside the tube.
So these are part of our motor system. These are copper coils that we had the design to actually create the propulsion wave that the vehicle would follow down. So when we built our facility, we needed about 3,000 of these individual coils.
The coils will be lined up along the middle of the track, where they can interact with magnets on the pod. Adjusting the flow of electricity through the coils creates different magnetic fields. Those in front pull the pod towards it, while those behind push it away. This pattern continues along the track, speeding up as the pod gets faster.
You basically send this electrical wave down the tube just like a surfer riding a wave. A surfer likes to stay at the top of the wave so that he gets the propulsion. So you're trying to synchronize those 2 fields, get up to whatever speed you're trying to go.
Alongside all the track components, yet another team are hard at work on the capsule to travel inside it, including structural engineering manager Helen Durden. First, they're building a sled which will eventually form the chassis of the capsule. But building a vehicle that's so new and untested poses a unique challenge.
What's been interesting is we start not knowing very much what it's going to wind up being. Like every other job I've had, it was spacecraft, aircraft. You have a lot of very well documented, solid standards. For this one, we went through all of it and got to pull what we think fits best, because this is somewhere between a car and a train and a plane. And maybe not a spacecraft, but NASA has really good open source docs, so we like to pull from those too. So that's a very unique thing with this, is really starting from scratch.
Once ready, the sled will be used to test the whole system for the first time.
There's always something pretty magical about seeing this design that it's always on my computer screen every day. Actually seeing it now here in aluminum and steel and welds and bolts, there's something, like for me, that's still a rush.
By May 2017, just 12 months after starting construction, enough of the track and sled were ready to test the overall Hyperloop. The individual components had all been shown to work on their own, but this would be the first time everything came together.
So it'd be one thing to build all of these individual pieces of technology in the lab. It's something completely different when you bring it all together and have to integrate the system. That level of risk with system integration, with the complexity that exists there, is really big.
Tube confirmed ready for test. Fire VFD and announcement test complete. Fire in 5, 4, 3, 2, 1, fire.
The whole vehicle lifted off. It was on magnetic levitation. It was using our propulsion system. That first test didn't go very far. It went around about 10, 15 meters or so, about 30 feet. But to be there with the group who put their blood, sweat, and tears and actually making this happen and see the elation on their face was something I'm never, ever, ever, ever going to forget.
They'd proved that the technology works, albeit at a leisurely 70 miles per hour. Next, they needed to push the system to its limits and demonstrate that Hyperloop really could be the fastest way to travel over ground.
3, 2, 1, fire.
The goals of the test after that were to go further and faster. There was a Saturday in July of 2017 where one of the most exciting days, if not the most exciting day of testing I ever had, we were just going faster and faster about every 2 hours. We would run a new test, a new test, a new test, and every test would go about 20 miles an hour faster.
The first time we got up to speed, I was just curled up in fetal position on a chair, like so terrified, but then it worked. It was pretty awesome.
Top speed we ultimately got up to was about 240 miles an hour, about 387 kilometers per hour, which is faster than the normal speed of high-speed rail. So we were able to do that very successfully, very quickly, and show that this could work.
The team had shown that Hyperloop could be faster than high-speed rail, even with only 1/3 of a mile to get up to speed. Next, they needed to show it was safe for passengers. First, they had to build the shell of an actual capsule on top of the metal chassis. This prototype pod would never carry passengers itself, but would take the team one step closer to that milestone.
We put this big shell on the outside, and that completely changed the characteristics of the vehicle. And so once we did this, we had to relearn how to control the vehicle. So with that vehicle, we got up to speed. We learned about the aerodynamics, even though there's not a lot of air in the tube, to ensure that this could actually work.
With the system now finely tuned, the engineers could start work on the passenger-carrying pod itself. The main challenge was to design a pressurized capsule that could withstand a vacuum, equivalent to being near the edge of space.
The next one actually needed to be a vessel safe for humans. So we started from scratch, built basically from the ground up a vehicle that could essentially fly at 200,000 feet of altitude. I mean, we built a spaceship. Over the course of about 1.5 years, we got it certified. We got it independently assessed to be safe so that myself and one of my colleagues, Sarah, could ride in it.
By November 2020, the capsule was ready for the world's first passenger Hyperloop ride.
I knew I had to be the first one. Starting this company, if it wasn't going to be safe enough for me, it wasn't going to be safe enough for anybody. It was way more excitement than nervous. And the excitement was to be sitting in essentially an idea. And there we were sitting in a Hyperloop that was kind of concepted on a whiteboard that you'd seen through ups and downs, you had nurtured, you had grown, you'd cried over, you'd done everything over. And here you were in the moment of like the most monumentous day in the history of the company, showing that it could work.
3, 2, 1, launch.
Yes. Yes. You feel this force, this acceleration. In this case, it's a little bit harder than normal, but it would be about like a performance sports car. It's about 0.6, 0.7 Gs or so, pushes you back into your seat. System gets up on the levitation. It was smooth. It was kind of unlike anything that I'd ever experienced before.
That was so good.
That was awesome. Oh my, that was awesome. The pride, the understanding of just how hard it was to get here was something that was humbling, to say the least, to be able to even ride in something that you've created in a new mode of transportation with everybody watching and safe, and it was surreal.
But despite reaching this huge milestone, Josh now faced a setback. The next step would be to build an even longer track capable of reaching true Hyperloop speeds. But when they ran the calculations, it became clear that the technology used in Nevada would not be economical over greater distances.
In the same way, Edison discovered 5,000 ways not to make a light bulb, we discovered a lot of things that we shouldn't make a Hyperloop like this. And so we had to reconstitute, re-architect our system to ensure that we could get to a price point that would allow us to deploy systems all over the world.
Building and maintaining the infrastructure to power the propulsion along hundreds of miles of tube would be too costly. One estimate for a Californian Hyperloop suggested the price could reach over $100 million per mile. And as technology inevitably improves, it would be a huge job to upgrade the entire network. To make Hyperloop a success, Josh needed a new approach. Then he was struck by inspiration.
I was actually riding up one of my favorite hills in the Santa Monica Mountains on my bike, and I saw this old 1933 Ford Roadster coming around a bend. And I was thinking that, isn't it crazy that that car's almost 100 years old and still driving on the road that we're driving on today? It's a really powerful concept. That's what's allowed us to see roads proliferate all over the world. And so what we want to do is create that same type of opportunity for Hyperloop, where we would have a dumb tube in a smart pod. So a pod 100 years from now would be able to go into a tube that we build today is a really big idea. It's something that ensures that what we build today won't become obsolete as new technology evolves. It will be able to incorporate new technology, upgrade, and ultimately be still relevant in a world of technology we can't even imagine.
Instead of installing miles of coils along the track for the propulsion system, Josh plans to design a pod that could propel itself, making the tube much simpler and cheaper to install. But before building another full-scale system, he needs his team to check it works efficiently.
If I gave you the analogy that a hamster you could let have a very big cage to run long distances and get his exercise, that's a way to do it. It's expensive. The other way is to put a little wheel inside, like a treadmill, so that hamster can get his workout by running on the treadmill. And so we took this approach that if we build something like a treadmill, something like a wheel that would spin to simulate the track moving, that we could actually gain a lot more from our test, a lot cheaper, a lot faster than if we built hundreds of yards of this tube.
Today, engineers Bunama Janya and Joo-hyun Kim are measuring the efficiency of the new propulsion system. The wheel represents the track, and the electric motor, which will make the wheel spin, is underneath. The motor will eventually be on the pod. To simulate a Hyperloop, the wheel must spin so fast that the test rig has been placed within a bunker for safety, in case any parts fly off.
Okay, set. So it's currently spinning, basically simulating the motion of the motor, which is a part of the propulsion system that we're actually testing.
Today, they're doing a low-speed test. The motor is spinning the wheel at 400 RPM, the equivalent of 110 miles per hour.
We are measuring how much power is going into the motor and how much torque is applied to the wheel. Then we can calculate how much power has been lost and how much energy has been actually transferred to the motion.
As a comparison, combustion engines are typically around 30% efficient. Josh needs this electric motor to be much more.
Stop recording.
Okay, recording stop.
At 400 RPM, the motor was 80% efficient. As the speed increases to 2,000 RPM, or 550 miles per hour, the team expect to reach over 90%. And unlike fuel-burning engines, they can recover the energy used for acceleration.
As the pod speed slows down, our motor actually turns into a generator. So it recuperates most of the energy to recharge batteries on the pod.
The new motor system is about 50% more efficient than any other type of motor out there. We have a system that's going about 3 times as fast as other maglev systems for about the same amount of energy. If we were to go the same speed, we'd be at about 1/3 or less the energy of a maglev system.
Virgin Hyperloop have shown that the technology is efficient and safe at high speeds. And they estimate that the simpler track would cost around 2/3 as much to build as a high-speed rail line, with much lower operating costs. But some in the industry believe they face bigger challenges than engineering and economics, such as gaining approval from governments and acquiring the land to build it on.
Hyperloop is a new means of transportation. So for that, we need new regulations. The process will take many years. Moreover, we need to go through a lot of different landowners to acquire this land. And this process takes a lot of time. As we see it in examples, building the highways or a new high-speed line in Europe, even though we have already the regulations being done for this mode of transportation, it might take up to 15 years, actually, to build this kind of infrastructure here.
Kasia Folianti is one of the founders of Nowomo, a Polish company that's approaching Hyperloop very differently. As well as planning a Hyperloop network, they're also designing a hybrid system that they believe can bridge the technology gap and bring Hyperloop to reality sooner. It's a high-speed levitating vehicle that could one day travel on existing railroad tracks alongside conventional trains, so no new land would be needed. It's called MagRail and can be used for passengers or cargo.
In MagRail, we are using 2 out of 3 main elements of the Hyperloop system, linear motor and magnetic levitation. If we are going to implement our MagRail technology much faster than the Hyperloop system might be implemented in Europe, we can already test these 2 elements and then prove that they are actually working, and afterwards they can be also implemented in the Hyperloop system.
The first full-scale MagRail system will be built along a disused railroad in southern Poland. The team are preparing to install the propulsion and levitation systems, a process they expect to ultimately cost around $5 million per mile, less than half the cost of conventional high-speed rail. Paweł Radziszewski is their Chief Technology Officer.
We will adapt the railway track by adding the linear motor in the middle and the levitation system on both sides. Linear motor allows MagRail vehicle to accelerate and decelerate, and levitation system allows us to basically soar above the infrastructure. We start on wheels, and then when we'll achieve about 40 miles per hour, we start to lift up and the vehicle moves without any friction.
As with Hyperloop, the levitating vehicles would use less energy than conventional trains despite going much faster, which reduces harmful emissions. And by floating above the tracks, there would also be less noise pollution.
We need to measure the railway track in order to make sure that it will fit our requirements, which basically must be very accurate for MagRail system.
Meanwhile, in Warsaw, another team, including engineer Natalia Strava, are testing the propulsion system with a half-scale test track.
The advantage of the propulsion system that we are developing is that it's much more energy efficient and allows us to obtain higher speeds. To fit the MagRail technology into the existing railway infrastructure was quite challenging because there is no much space between the rails to put something there, and we needed to add some additional components. So it took us quite a lot of time to figure out how to do it.
The electric propulsion technology between the rails is secret and cannot be filmed. Natalia's team are testing the new software that delivers power to segments of the track and should ensure a comfortable ride for future passengers, while also saving energy.
We want the passing between segments to be smooth, and we want to keep continuous thrust. There is an issue with passing through the segments because it's not so easy to keep continuous thrust. So we developed very advanced control algorithms that take care of it.
This hybrid system would be simpler, cheaper, and faster to build than Hyperloop, and can still reach speeds of up to 340 miles per hour, according to Nowomo. They hope to make this next-generation transportation a reality by 2025, with their full-speed Hyperloop reaching 740 miles per hour, following in another decade.
MagRail technology is the first step to implementing Hyperloop. In the second stage, we want to add tubes, which will remove air from the equation, and then we can achieve even faster speeds because we don't have aerodynamic drag. And we want to keep continuous thrust. There is an issue with passing through segments because it's not so easy to keep continuous thrust. So we developed very advanced control algorithms that
The MagRail and Hyperloop technology being developed today could replace aircraft for popular routes all over the world, potentially saving millions of tons of carbon emissions every year. But many of the longest journeys by air fly over water. So researchers are now investigating the very limits of how far Hyperloop can take us, whether it could ever be possible to span oceans.
We see in the last couple of years that people are tending to travel a lot, especially between cities along the coast or in coastal areas. So a connection is very important between continents. And there were up to 3,000 flights each day that could be replaced by a Hyperloop connection. So it would be beneficial for the future when we want to lower our carbon footprint and still have the benefits of traveling.
In 2019, project manager Linda Kemp set out to test how storm waves might affect a Hyperloop tunnel crossing the Atlantic Ocean. They designed an experiment in one of the largest marine testing basins in Europe, at the research center Marin in the Netherlands.
This basin is 170 meters long, so we're choosing to scale it down and to make sure that we have something that fits into the basin, but you also want a model to be long enough to see the impact of your test results.
Linda's team constructed a model of a Hyperloop tube that's 110 times smaller than the real thing would be. The tube represents a 10-mile-long section of the full-size tunnel, submerged the equivalent of 150 feet beneath the surface. Once everything was in place, the paddle started up to simulate a storm, mimicking monster waves that would be up to 130 feet tall.
It's a really exciting moment when the first wave is running into you. The most extreme situation was an Atlantic storm that just happens one every 1,000 years. And you really want a structure to be capable of still being there after such kind of wave. So we're testing these kind of waves to see if a structure like this could handle these waves.
Under the surface, cameras monitored the precise position of LED lights on the tube to detect any bending. And instruments recorded the tension on the mooring lines.
We expected that when the waves are running over the tunnel, that it would bend with the waves. So it would be lifted and it would go back again. That's something that you don't want when it's a Hyperloop.
But as the waves interacted with the tube, something surprising happened.
We saw that the bending was even higher than we expected. The tunnel was lifted up to the free surface. So the forces due to the waves, they take it up and lifted it. And then it was just a floating tunnel that was piercing through the surface. And it was bending there as well.
Floating to the surface in a storm would be disastrous for a real oceanic Hyperloop, damaging the infrastructure and potentially colliding with ships. Linda ran the storm waves a second time with the tunnel now submerged at twice the depth, the equivalent of 300 feet deep. This time, as the waves thundered over the tube, it stayed underwater, moving only a small amount.
The waves weren't impacting the tunnel that much on the 100 meters water depth. So movements and accelerations are smaller there.
Many other factors, such as the impact on marine life, still need to be investigated. But Linda had shown that even the most powerful Atlantic storms shouldn't prevent a connection between Europe and America.
So we concluded that it would be good to consider to have even more larger submergence depths for really safe travel, because I think when you're talking about transportation through a tube like this, is that you really want something stable.
Hyperloops may one day carry passengers deep under the surface of the oceans, connecting Asia to North America's west coast, the east coast to Europe, South America to Africa. you could travel the world in hours without ever stepping on a plane. But while these ocean-crossing tubes are still the stuff of dreams, the race is already on to build the world's first commercial-scale Hyperloop on land.
We're at a point now where it's not a matter of if there will be Hyperloops. It's a matter of when there will be Hyperloops. You can imagine that you would see Hyperloop routes throughout the world. Asia, North America, South America, Europe, Australia. I think we'll see a world where we have Hyperloops on every continent.
The population is growing, and we need to meet the needs of this higher demand. Hyperloop is actually the only solution. Most importantly, this is the most sustainable solution that we have at the moment.
We know the technology can work now, and it's about how can we deploy the technology to showcase its benefits and its potential as quickly as possible. I like to say that this is the decade of Hyperloop. It started with Sarah and I being the first two people to ride a Hyperloop. It's going to end with hundreds of millions of people riding a Hyperloop. It's a world with a fundamentally different transportation system. And that's something that's actually tremendously exciting.